Hi all, this is Lakshmi working as assistant professor in the Department of ECE at SNSCT. So today I'm here to discuss about the lecture series on electronic circuits where the unit is BJT and FET biasing. So here in this topic we are going to discuss in detail about one of the biasing technique, which is fixed biasing method. So before dealing about the fixed bias technique, so here we must know about the term biasing. So the biasing means it is the process of supplying external voltage to a device for its proper functioning. So this is called biasing. So to be more technical, we can define biasing as it is the DC voltage which is applied to a device in order to turn it on so that it can amplify the AC signal. So the process of biasing means it is applying external voltage to a device for its proper functioning. So we know that there are three regions of operation in BJT. So in the previous lecture series, we have discussed about the BJT working and its types. So we know about the PNP and NPN transistors. So here I have given the PNP and NPN. So there are three regions of operation. So one is active or linear region. So in this region, active region, we could see that here the base emitter junction. So this is the base emitter junction. So this junction is forward biased and the base collector junction will be reverse biased. So this type of connection, when it is given, the transistor is said to be in active region where the transistor is going to work as an amplifier. And the next is cutoff region. So in cutoff region, here the base emitter junction. So this one is for PNP. So similarly for NPN, here the polarity alone gets reversed. So for cutoff region, we can see that the base emitter junction is reverse bias. So which means there is no current flowing through the circuit, and in this region the transistor is going to act as a open switch. Okay, and the next one is saturation region. So in this case we could see that the base emitter junction is forward bias and the base collector junction is forward bias. Here when both these junction, that is JE and JC, when these both are forward bias, the transistor is going to operate in a saturation region, which means that it is going to operate as a closed switch. So here in these two regions, cutoff and saturation region, the transistor will be acting as on switch and off switch. So open circuit and closed circuit. So this is all about three regions of operation of a transistor. So there are various types of biasing circuits. So first one is fixed bias, emitter stabilized, voltage divider bias and DC bias with voltage feedback. So these are the four different types of DC biasing circuits. So now we are going to discuss in detail about the fixed bias circuit. So this is the circuit of a fixed bias configuration. So here we can see that this transistor RB plays the role here in adjusting the value of the input current, which is our base current. So we could see that the single supply is given to both base and collector terminal. So by adjusting the value of this RB, by adjusting the value of RB, you can adjust the value of IB. In turn, we can adjust our output current, that is collector current. So this single supply is given to both the terminals, base and collector, whereby this RB can be changed by, we can change this to adjust our IB values. So this is the circuit of the fixed bias in BJT. So now let us do the DC analysis of this circuit to calculate the various parameters of a base current, collector current, etc. So To do the DC analysis, what I'm going to do here is I'm going to first remove my DC source, that is VCC. So by removing this, how my circuit looks. So this is how my circuit looks. This is called my DC equivalent circuit for fixed bias. So what I have done here is the DC source has been removed, and we have the RB, so which controls the value of IB, which in turn controls our IC. So but this type of circuit is not much stable compared to the other type of biasing. There occur stability issues due to the variations in the temperature, which affects the collector current. So here now we are going to analyze the input circuit and the output circuit separately. I am here considering my base emitter loop, which is my input circuit. So here I am going to do the analysis and calculate my value for IB. So we know the well-known law, that is Kirchhoff's voltage law, which indicates that the sum of voltages around the closed loop is equal to 0. So by applying KVL in this loop, you could see here it is mentioned. So we would get the equation as VCC minus IB/RB, that is the potential drop across this RB is IB/RB minus VBE is equal to 0. So when we solve this equation, we would obtain the value for base current, that is IB, which is equal to VCC minus VBE by RB. So this is how we calculate the IB value. So similarly, I'm going to do the analysis for my collector emitter loop, which is the output loop. So this is the collector emitter loop. So here I have considered my output part, and my collector current here is given by in terms of beta. I can relate the base and collector current as, so we know that is the beta is always equal to IC by IB. So with that relation, IC is equal to beta IB. So similarly, applying Kirchhoff's voltage law in the output part, I would obtain the KVL equation as we can see VCE plus ICRC, which is the potential drop here across the collector current, that is across the resistor RC, minus VCC gives you 0. So from this I can calculate the value for VCE. So, as I told, there is a stability issue in this type of circuit. So, in order to improve the stability, what we are doing is I'm just adding the value of emitter resistance in my emitter part, which would stabilize my circuit, and thereby it would improve the stability. So, you call this as emitter stabilized biasing. So when we consider the emitter bias stabilizing, so here again I'm considering my input part and output part separately, and I'm doing the analysis by applying KVL. I can solve for the value of IB. So when I consider this loop, so when I apply KVL, what would I obtain is VCC minus IB/RB minus VBE, and including this emitter part, IERE will be equal to 0. Then solving for the equation of IB, I would get this value. So we could see that here the beta is the current amplification factor. So this is, indicates that the stability has been improved. Similarly, analyzing the output part of the emitter stabilized circuit, we can solve for VCE by applying the KVL, Kirchhoff's voltage law. The equation obtained would be IERE plus VCE plus ICRC minus VCC equal to 0. Then solving for VCE, we would obtain the equation. So today's assessment is discuss the disadvantages of fixed bias. So as I told, the stability is poor as there would be a variation in the collector current as heat development cannot be stopped. And the stability factor is very high. So there are strong chances of thermal runaway which would destroy the transistor. Hence this method is rarely employed. Thank you.